transform study. So previous lecture, I posted a lecture note for you. It was called lecture number 2, which there I described what is the source of the Laplace transformation, basically a time function that is changed through a specific integral into an S variable, where S is being a complex number. It is a very useful tool in general analysis. So we saw various Laplace transform scenarios. Generally, the main issue is to have a table available which contains the time functions, a list of standard time functions, and their transforms. This has been done in a table. So in order to go from a time function into a Laplace domain, all you have to do is to get your time function and look up in the table and post the Laplace for the function. And if the functions are adding, the Laplaces are adding. That's a simple arrangement. So you can get functions. You can create functions of Laplace. However, it gets a little bit more involved, more difficult when you want to go into a reverse. The exact function may not be found in the table in order to translate it into a time. So you have to resort to taking the functions and breaking them down. This process is called partial fractioning. It is a basic algebraic process. There are many ways of doing it. I tried to illustrate that for you by bringing up different cases and as how you will you can determine the partial fractions forms. So once you partial fraction to a standard forms, you have to adjust them. You have to adjust zeros, usually numerators, in order to find their inverse identically in the Laplace transform table. So you have to build them into adding blocks and then inverse transforming throughout by looking up in the table and then taking the whole function back into the time domain. So that was the process which I explained in lecture number 2. So today I have posted for you 2 items on Blackboard. Number 1, it is lecture 3. That's the subject of today, which I hope all of you will have available. It is a 7-page lecture note. There you will have the specific application of the Laplace to circuit analysis, and with examples, which today I'm going to go over it with you. And then you have another thing that was posted. It was the solution to homework number 7. I gave you as an assignment. So I solved all the problems. I showed how it can be done step by step, and it was also a 7-page document. Actually, the first page document was 9-page. Sequentially, it went through 1 to 7, and then I decided to add 2 more. So I wrote it 7 plus 1, 7 plus 2. So the first one was actually a 9-page document. The second one is, however, a 7-page document. So I began posting it onto Blackboard under the syllabus tab, because that's the place everything is listed. So I was posting. By the time I got to page number 7, by page number 7 of homework number 7, the system refused to upload. So naturally, I hit the capacity quota. So 1 page was left out. That is page number 7 of the one that is titled ECE 2101 Homework 7 Solution. This was left out, 1 page. I'll tell you where to find it. So I decided to put that into your email, that last 1 single page. And I explained, go and add it to the pack of homework number 7. All of you should be able to go to your email and then find it. I send out a mass email for that. So retrieve your page 7 of this document, of this heading, in your email. That's the last page of homework solution. In the homework solution, I did all of the Laplace, which is the essential part. In the convolution part, which today I will, if I get the time, I will briefly explain it. I did one convolution problem for you, and I left the second one out, just to give you an idea of what the convolution is and what's the meaning of the convolution, where it comes handy. Okay, so let us begin with lecture 3 notes, beginning with page 1 of the 7, and we are utilizing Laplace properties in order to perform circuit analysis. That's the main issue. You should be able to do circuit analysis. Okay, so the important property of the Laplace. One of the properties of the Laplace is about the derivatives. If Laplace of a function y of t is denoted by y of s, which is undergone through this integration, shorthand for that integral is post an L in front of y as an operator, Laplace operator. So L in front of y, it means we are transforming y. L minus 1 against the y, it means we are inverse transforming. It shouldn't be y, of course, the y of s. L minus 1 applied to the y of s, it means we are changing it from s domain into time. So here, if y of s is the Laplace transform of y of t, then the Laplace transform of the derivative of y, it means just the derivative put under the integral. If you did that, it will be equal to s times y of s. So it will be s multiplied by the Laplace of the y minus y, initial value of y in the time domain. That is at time t equal to 0 minus here. That's the 0 minus here. So if a system has an initial condition, of course, it will be just s times y of s minus y of 0. That's one of the important properties. Next one, second derivative. Laplace transform of the second derivative of a function y, where the Laplace of y is known, is s squared multiplied by y of s minus s times multiplied by y of 0 minus the initial value of the function times 0 minus the initial value of derivative of that function at the time 0. So these are kind of real-time information, initial values, real-time information. So, for example, in the case of mechanics, real-time information about a trajectory would be x0, the origin, time 0, and then initial velocity, v of the 0 minus. These are kind of two initial conditions for mechanical things. This is therefore y of 0 and s times y of 0 and minus y dash of 0 minus. However, when a system happens to have no initial condition, 0 initial condition, beginning from the 0 energy or beginning from the rest, these two transforms become extremely simple. Look what will happen. Those terms will drop out because the initial values will be 0. And only, easy to remember, that Laplace of derivative is s times the function itself. If you have the function, you have Laplace of the function, then Laplace of its derivative will be s times the function. Laplace of
second derivative would be s squared times. This is kind of the simplified version. If the system happened to have no initial condition, zero initial condition. It appears with the initial condition of zero, like d by dt acts like an S operator. So if you're differentiating something by d by dt, a time function, all you have to do is to take the function and multiply by s. The function Laplace, the Laplace of the function multiplied by s. So you will get the derivative of that function, provided the initial condition is zero. Comes very handy in differential equation solution. This is our foundation for the properties of Laplace transform. And now let us jump into the circuits. Our three elements: resistors, inductors, capacitors. If you recall, each one had a current, each one had a voltage, and there was a derivative relating current to voltage for both inductor and the capacitor. And there was just proportionality R connecting current of the resistor to the voltage. So I'm going to generate the Laplace models for all these three elements. It is in the handout, it is summarized, it is also in your book. Okay, so let me erase the board and get started. Okay. There is a concept called impedance. If you happen to have a, what is impedance? What is impedance? If you happen to have a circuit that you have a current applied to it and a voltage is applied to that, provided that the initial condition within circuit is zero, initial condition is zero, then the V of S, Laplace of the voltage divided by the Laplace of the current waveform comes up to Z of S, becomes a function of S. Z of S is called the complex impedance of a circuit. So if this circuit contained capacitors, inductors, here and there, many of them, as many, resistors, etc., linear elements, and provided all of these inductors, capacitors had an initial condition of zero, meaning that the capacitor voltages were all zero, inductor currents were all zero at the time zero minus, then one can derive Laplace of the voltage to the Laplace of the current in terms of a complex function called the Laplace impedance. So we're going to see how we can create that Laplace impedance. First, we're going to start with the general cases. Okay, number one, resistor. Simplest of all. For a resistor, we know that I of t and V of t here, regardless it is alternating or whatever, they're related with an R. So V of t is just R times I of t, because both are functions of time. R is only a multiplier, it's a scalar, it's not derivative, it's just a constant. So this shows you that the Laplace transform of V of t is equal to R times Laplace transform of I of t. Because R is a constant, it comes out. Therefore, V of S
is going to be R times I of S, where I of S is the Laplace of the current. Therefore, here you are, V of S over I of S turns to be just R. Same old thing. Remember the impedance in the frequency domain? Z of R was just R, no complex notation. So we got it. This is the, you can call ZS of R, impedance of R. It's just a number. Next, inductor. Inductor. Okay, in an inductor, the relationship here, if a voltage is applied to an inductor under V of t, if I is the current in the inductor, L the inductance, then we know that induced voltage is L times rate of change of current. This is the classic formula, which explains voltage appears when current changes in an inductor because a change of current changes magnetic flux, and variation of magnetic flux induces a voltage. That's what it is. So here, if you take that line and you Laplace transform the P of t, you will have the L times Laplace transform of L multiplied by Laplace transform of di by dt. Okay. But Laplace transform of the di by dt, we have it from the properties. Laplace of V of t will be V of S. This will be L times S times I of S minus I of 0 minus the initial value of the current in the inductor. There it is. You get this expression here. Yes, if you have an initial value for the inductor, an initial current, this would be the relationship defining voltage in terms of the Laplace of the current. There are involved. You have L, you put the complex S, and you have a number here, which is initial current. Now, what if initial current was 0? Okay, if I was 0, I of 0 minus was 0, no energy initially, then automatically you would get Vs over Is equal to Ls. This would be the Z L of S. This would be the definition of impedance of an inductor. S times L times S. So if you have a circuit with an inductor, assuming the initial current in the inductor is 0, sometimes you can do that in circuit analysis, then the Laplace of the voltage to the current can come out easily as a ratio, a very nice ratio. And therefore you can present it with a very simple relationship. That Z of L is Ls. So we'll show L times S as an impedance. Again, try to relate it to the J omega L in the AC circuits. We had J omega multiplied by L. Here you have S multiplied by L. Let me tell you what. If for S you substitute, if you could substitute J omega, you make such a substitution, automatically it's going to yield the frequency impedances. The frequency impedances. Which frequency? The frequency of omega. Then what is the meaning of V? Then V is not a general voltage, but the V would be the phasor voltage, the alternating AC voltage, the cosine functions. And you would I would be the phasor current, the one that we studied. Fortunately, we had time to do it in the class sufficiently. So that would be the phasors, alternating voltage and the current phasors with frequencies and phase angles. If you substitute S equal to J omega. So that is the relationship between the S domain and the J omega domain. Very handy. S is more general and it can be switched easily into a frequency domain without additional calculation. So this is the general equation, the one that I put a star on it, with initial condition here. I put another double star on it with initial condition. However, if you don't have initial condition, 0, then it is even simpler. It's just LS. The first product only counts. And you can come up with the impedance concept. However, I did examples, however, with the initial values, just like the way that, the book did it. I gave you some examples. There are models that we need to create for the initial condition. And here are the models. It is listed in page 1. This is called the models, Laplace models. Laplace models. Okay. In order to present this equation here and V in the form of a circuit, you have, excuse me, you have two options. One would be the series. So look at the picture number 1. Here is the inductor. We can imagine that there is a minus and a plus, a DC voltage source. The size of the DC voltage source is L times I of the 0 minus. So whatever initial condition is, you multiply by L. Say, if initial condition for the current was traveling in that direction, I of S was traveling in that direction, the polarity of that battery is negative, positive, and this is a voltage across the combination here, V of S. Where this one is L times S. For the inductor, you will put the LS. Now, LS is the impedance of the inductor without the energy. It's the one that I just explained. So here, this relationship will exist between the circuit law that you apply here. Simply apply the potential law, KVL, go from here to there, Li0, go from here to there. It will be Is times Ls, and then go from here to low, minus Vs. It will be that line, basically. So this is the series model presentation of energized inductor. Series presentation. Alternative to that model is another representation called the parallel representation, which is that one. A current source, a constant current source of a value equal to I0 of minus divided by an S. So a constant current will be added in here of such value, I of 0 over S, while the voltage is V of S, and the current going in is I of S. So you have two options there to choose this model or that model if you had initial condition, if you had this initial condition. Which model would you choose? Whichever you choose, and you apply circuit laws, the answer will be the same in the end. So it doesn't matter which one you choose. But often, one choice, whether parallel or the series, will adapt itself easier to the circuit format, to the rest of the components. For example, if you see there are other series elements there, like capacitors and so on, I would go for that one. I won't take my series, naturally existing series circuit, and then choose this model for analyzing it. Common sense says, you just go by the simplest of all. So this is it.
Laplace transform of the inductor, for this inductor. It is explained from its fundamental equation and its transformation, properties of Laplace, and derivation of their equivalent models. Next, the capacitor. So you go to the next page, capacitor. Let's erase this. For the capacitor, the law is if you apply any voltage to a capacitor, if I of t is capacitor voltage, V of t is the applied voltage, then I of t is C times dV by dt. C multiplied by rate of change of voltage. That's the general formula for all capacitors in time domain. However, if you Laplace transform that line, this simple so-called differential equation, you will end up having the I of s, that's the Laplace of I, is C times multiplied by Laplace of derivative. So it will be S times Laplace of voltage itself minus initial voltage of the capacitor. That's it. This is the complete line for a capacitor with possessing an initial value on it. Now, capacitor impedance. Vs over Is ratio can be created as a function at this point if your initial condition was 0. So, assuming if V of 0, V of the 0 minus was 0, that is initial condition was 0, then the ratio of V of s to I of s will give us a quantity called 1 upon Cs, which is known as Zc of s, impedance of the capacitor. Please compare that against the 1 over j omega c. 1 over j omega c. So it looks like as if you're substituting s equal to j omega in the Laplace impedance. It's very similar to that one. So frequencies can be deduced from the Laplace domain very easily by switching from s into j omega. The sometimes opposite is also possible. That if you have a j omega, you may switch that, but you have to be, very skilled in doing that. If you have a j omega, you can replace every unit of j omega by an s. It's kind of, automatic and quick transformation between frequency and s domain. Okay, let's put it this way. Concentrate on the Laplace. This would be Laplace impedance. Impedance has a meaning if the initial condition is 0, because you can get the ratio. However, if the initial condition is not 0 and you're solving a circuit that it possesses initial energies here and there, then we need to model that equation, just like before. So these are the standard models of the capacitor. Here, you have C, a voltage source. Then you have I of s, that's the Laplace of current, series current, and that's the series model. In the model, you have an impedance here,
1 upon CS, which is that impedance. And you have in series with a constant voltage source. The value of that would be V of 0 minus upon S. So treat it as a constant voltage source within the circuit, but the constant voltage of the source does have a S in the denominator of that. So this will be the series model. Series equivalent circuit, you can call it, model or the circuit. V of S is the voltage, plus minus total of S from end to end. Try it. Apply a voltage law, kind of a KVL law around the loop. This is the IS. So IS multiplied by the impedance. IS multiplied by 1 over CS. That's the voltage drop on that one. So keep going up, go up. That's V of 0 over S plus IS times 1 over CS minus VS equal to 0. That's the KVL. It will come to that line exactly. The other option is the parallel presentation of that equation. This equation can be presented in a parallel form as 1 upon CS there. Here, a constant current source heading in the direction of the arrow. I of S will be the current through the capacitor, and the value of this current source would be C times I of V of 0 minus. C multiplied by V of the 0 minus as a constant current source feeding between these two parts, feeding parallel with the unenergized capacitor. Again, if the initial condition was 0, notice what will happen. This source will disappear. You have just a capacitor, that's the impedance. This current source would disappear. So that will be an open, it will be just the impedance. So it will be the simplified case, which is, the common situation for analysis. Now, once you have devised for each one of these capacitors and inductors and resistors, their models. For resistor, simply it was a proportionality, just R. You can perform circuit analysis, applying all the rules that you learned about KVL, KCL, impedance, voltage, current multiplied by the impedance is the voltage, etc., etc. So all the analysis that you did in the DC and we carried over to the AC can be carried over to the Laplace. Same procedure, same techniques. And now the rest is, having given all those models, let us get busy solving with examples. That's the only way we can, gain a little bit of hands-on experience with problem solving. So this is a set of situation which involves initial conditions. I deliberately came up with initial conditions so that we can do that, and then later we will study the zero initial condition, which is piece of cake under the transfer functions. Okay, example number 1. Okay, let's see what we have. Example number 1, analyzing a circuit including all initial conditions. Incidentally, this problem is extracted from from the textbook. Reference is 15.5. I think they had the answers there, but no calculation. I'm just showing you how you calculate. So here is the problem. You have a 12 volt, R1 equal to 2 ohm. There's a switch there. It's open initially. And then that switch will close at the time t equal to 0. Switch. You have inductor L equal to 4 Henry. You have a resistor following that, R2 equal to 2 ohm. Another resistor here, R3 equal to 2 ohm, equal to 2 ohm, and the capacitor C equal to 1/3 of a farad. Okay. So the switch is open. The circuit is at rest, at steady state condition. In other words, the same old story. Inductors are short circuit at the steady state because battery is a steady state. Capacitors are open circuit. Being a short, it doesn't mean its current is 0. There must be a current running through it because you have a circuit. So a current is going through it. Capacitor being open circuit doesn't mean that there is no voltage on it. There can be a voltage on it because there is a voltage on the resistor R3. As the current goes through the R3, it will establish a potential across the R3, which will transfer that to the plates, and therefore will initialize the capacitor voltage. So let's see what we have right now before closing the switch. Plus minus V 0 of minus. I can deduce that amount while it is open only a moment before closing. So 0 minus means just before closing this. So the steady state condition is still holding. There must be a current going through the inductor just before closure of that switch. We can predict it from simply circuit inspection. So here's how to inspect. Step 1. So here's how to predict that. It is basically DC balances. Take inductors for short, take capacitors for open, then you have 12 volt, R1, R2, R3, they're all equal, you can see that. So immediately you can say I of 0 minus, this is the moment for t equal to 0 or minus. I of 0 minus is equal to 12 volt divided by R1 plus R2 plus R3, they're all in series. And this adds up to 2 amp. 2 amp. That's 6 ohm, 12 over 6 ohm, that's 2 amps. Voltage. Voltage of capacitor at that moment is going to be the voltage of the resistor R3. So you know the current of R3, multiply the 2 amp by R3, then you get VO of 0 minus is equal to V of R3 is 2 amp times 2 ohms, that's 4 volt. There you are. This will be the initial voltage across the capacitor. So we are equipped at this point with initial values. Then next thing is to create the model, the complete model. Okay. Step 2. Draw the Laplace impedance, Laplace impedances accounting for initial conditions. It means go and use the models. To use series or parallel options, remember, it's hinting at, will depend upon the circuit format.
Yes, the way that they're organized will tell you which way you can which one you will choose. However, I stress on this: whichever you choose, the series or the parallel, the answer will be the same if you play with the circuit laws correctly. The same answer will come. Now we choose the following option. Now the switch is closed. T is equal to greater than 0. Let's say greater than 0. If for time t equal to 0 or greater or equal to 0, the switch is closed. Once the switch closes, it goes into that position. Please note that to the left of this line, nothing counts because it's like a short circuit. It becomes out of commission. What do you have here is the following. You have a short through the switch. Then you have the inductor. Then you will post the DC voltage, which is Li of 0 minus. And remember, heading of the current was that way. And then you will post for Ls the value of 4S. So this becomes Li of 0 minus. L is 4 Henry, so the 4 has to multiply with 2, making it into 8. 8 plus minus, so it's 8 constant. Then you have R2 equal to 2O. Then the R3, which is also equal to 2O. Then you will have the capacitor. For the capacitor, you can account by 3 over S. This will be the impedance of the capacitor. Excuse me. Impedance of the capacitor. This is 1 over CS. And then it's the series voltage source here, plus, minus. The series voltage source for that sense of the current is going to be equal to V of 0 minus over S. So you will go seek for the 0 minus 4 divided by S. So this will be 4 over S. Let's pick that point as the 0 volt reference. And now we need to calculate what is voltage here, VO of S. In other words, we want to know what is this VO of T, the function of time. Objective of the problem is to, given the initial condition, to calculate voltage of that resistor. We used to do this with differential equations. But remember, our differential equations were limited to series form or parallel form. This technique allows you to do more. You can do more with that because we have series, the two series, then parallel with this, then parallel with that. Kind of more complex. Okay, how do you set up the equation? You don't need anything else. All you need is that. However, if in a certain circuit initial condition was non-existent, the circuit simplifies dramatically. This source goes out, it's just a short. For the inductor, you will put just 4S. This would go out. For the battery here, you won't have any more V0. It will be like just nothing. Capacitor would be there, 3 over S. The circuit would simplify considerably without initial conditions. But we are trying to be realistic. There was the problem, switch was open, now you're closed. This is a pretty serious problem and we're trying to solve it. Okay.
Once you get that circuit, this is your Laplace circuit. That's the great part of the problem, you know, like you get major points coming up to this point. The next thing is circuit analysis. Pretend that you are doing whichever analysis you want, DC analysis. You're doing node analysis. You're interested in the node voltage here. So we target that node voltage. This is the ground node, 0. And we're going to write the nodal currents. Current going that way, current going this way, current going that way. That's the node equation at that point. Adding the whole thing into 2 0. Okay, so let me write that nodal equation. You have it right in front of you. So let me just erase the top part. Okay, there you are. So this will be our nodal equation. We want to calculate what current going in this direction of the arrow, in that direction. So I need, the voltage here is 0, obviously, because it is connected through the switch. So that is a 0 volt. So you need to calculate overall voltage that drops over these series elements. What is overall voltage? That's a positive, that's a negative. So the net voltage from there to there is the O of S, a -8, divided by the sum of the two. So you get 2 plus 4S. Okay, got that. However, if you don't like the order, because it is series, you can change. Take this battery, slide it down here. So the bottom of the battery will level with the 0. Top of the battery will show 8. Then leave the inductor and R in series. So you've got to, in order to measure the potential drop from here to there, you need to subtract VO minus of 8, letting the current go that way. So this will be the, excuse me, this will be the current flowing in that branch. Of course, which current? It's the Laplace current. Plus, voltage is there, Laplace voltage, divided by R3, that's 2. This will give you the current going down there. Next, current going in the direction away from that node is voltage here, VO of S, minus voltage there, which is 4 over S. Divided by 3 over S. This is the impedance, just like complex resistance, impedance. All of that adds. That's it. This is the major part of your equation. This is your equation setup. Look what you don't have here. You don't have the O of S. So calculate. The O of S will come up to be, from that, you have to solve it 4 times S plus 2. I need to hold with one hand. S plus 2 divided by S squared plus 2S plus 1.5. 2S plus 1.5. All right. That's the main thing. If you get to that point, that's great with the correct answer here. It means that you managed to determine the Laplace transform of the voltage under the question. This is the Laplace transform. How can we return that back into time domain? We go from here back into time domain, you're not going to find that function exactly the way it comes out, like 99.99% of cases. You need to convert it, kind of organized. So let's see how we can do that. So you will take that function, first of all, check one important thing. Ask this question about the denominator. This is the second order. You have two poles, because if you equate to 0 and you solve it, by definition, it gives you the poles. You have two poles. Question is this: if the two poles were real, two distinct real values, it would be piece of cake, the easy case, case one. If the poles were duplicate, like s plus 8 squared, for example, if this was 1, it would be a perfect square, then you have a duplicate poles. There is another way of breaking down that function for duplicate poles. In our case, our poles are complex. How do you know? Get the delta of the function of the second order, quadratic. So 2 squared is 4. Minus 4 times 1.5 times 1. So it is 4 minus 6. Okay. Square root of 4 minus 6, that's an imaginary number. So you have complex poles. For complex poles, generally speaking, you need to factor out your function in a generalized form of s plus a plus omega squared, s plus a, and a combination of that, and omega over squared, of course, s plus a squared plus omega squared. This is the trick of the trade. There are two ways of doing it. See, we need to take that function with algebraic tricks, algebraic skills. It's just algebra. Convert that, or kind of, reformat it, basically, into the summation of two functions. Denominators will be shared the same way, s plus 8 squared, omega squared. But the numerators need to be separated. You do this by simply adding or taking, subtracting certain amount until it formats itself compatible with this shape, with that arrangement. You have to create a term of s plus a in the numerator. You have a square of that in the denominator. You need to create an omega, a constant, say here, matching the square root of that term. Okay, I emphasize on that because that's the way these things work. I showed you how to do that. The first step that you will work is denominator. Don't look at the numerator initially. Simply work on the denominator. It gives you the clue. So put your focus on that one. This can be written as s plus 1 squared plus 1 over radical 2 squared. Go back and check it. See if it is correct. Here. You get s squared, twice of that times that, 2s. Then you get 1 squared, 1. 1 upon radical 2 squared is 1/2. 1 and 1/2 is 1.5. Once you come up with the balance, there are two informations that will come out of it. Number one, you will figure what is a, so you will know what will be the target in the numerator, what you're going to create in the numerator. Next, you will look into the second term and you will figure what is omega. Then you will know what to create in the second function. So this function is going to split right into two parts, two of these. into those two formats. With a little exercise, you can master that, but that's the way to do it. That's the way to do it, and there's no other way of, explaining it. So we will start working once you have the denominator. It's almost like a kind of algebra artwork. Let's put it this way. So here's what will come out of it. I took 4 to the denominator here to clean the field a little bit, because I want to leave s plus 2, s squared, you get plus s plus, you have 1 squared, and then you have 1 over radical 2 squared. Okay, I have s plus 2. Look, I have s plus 1. I'm going to borrow 1 from this one and split it into a 1 and 1. S plus 1 and a 1. Okay, this is the algebraic artwork, as I said. The numerator balance is not affected. I reserved 4 into the denominator, but I should not forget it. Don't forget you have something here. So it is ready to break up right in the middle here. So break it up. Then you will have the O of s over 4 is equal to s plus 1 over s plus 1 squared plus 1 upon radical 2 squared. Next is going to be 1 over, go to the next page. The next one is going to be here, radical 2, 1 over radical 2 over s plus 1 squared 1 upon radical 2 squared. You're getting into the other picture here. All right. So what I did, remember it was a 1 in here. I created this omega. That's why suddenly 1 upon radical 2 appeared in the numerator, because I want to match this omega. But in order to keep the balance, I need to multiply that by radical 2. So radical 2 times 1 upon radical 2 is still 1. So I have not changed. I have not changed the weight of my function. It is ready to go into the table. One by one, start inverse transform. So this will be 1/4 inverse transform of VO of S. It comes handy, this notation. L to the minus 1, inverse transform of V of S, then inverse transform of S plus 1 squared plus 1 upon radical 2 squared, and then added to radical 2, that's a multiplier, inverse transform of 1 upon radical 2 over S plus 1 squared plus 1 upon radical 2 squared. Okay, now, all these inverse transforms can be looked up in the table. So if you look up, this will be 1/4 of VO of t, the final answer. This term will add up to e to the power minus at, which is t, cosine of 1 upon radical 2 t, plus radical 2 e to the power minus t sine of 1 upon radical 2 t. And don't forget to send 4 to the front, multiply throughout by 4 in order to get the final answer. So you can remove 4 from here, multiply throughout, you post 4, there is your final answer. So I demonstrated for you how, with that example, how you can utilize the initial condition in a circuit in a maybe practical circuit, by throwing the switch, you can carry over that initial condition into the models for your capacitor inductor in the Laplace domain, build the circuit, apply nodal analysis as if you're doing nodal analysis for DCs, except you're utilizing Laplace impedances at some constants within the circuit. You have to be aware of those constants. So this is the way to solve the values. Now, example 2. So I gave an example 2. It's kind of an easy example. Okay, let's see how we can solve that one. 4 or 5. Let me see what we have here. Okay, yeah. This is the kind that is easier than that one. Example 2. So you have a circuit. The voltage is changed from 5 volt, is then stepped up to 10 volt. This is the E of t, an input voltage. That's the time axis. The circuit is a very simple R and an L, and another R, and that's the function E of t. Okay, and we need to calculate, of course. We need to determine V of t. This is what we want. This is probably a lot here. Okay. V of the t. Now let me see if the whiteboard is still in the picture. Yes, still is in the picture. So we want to solve that one. It's a 2 L is 2 Henry. This is a 2 Henry and 1 ohm. First thing to do is, what is I of 0 minus? We need to calculate the I of 0 minus. So here, steady. So it has been there, that 5 volt has been here for the longest time. So everything has come to rest at that point. Then suddenly that 5 here is stepped to 10 volt. The 5 volt steady voltage there sets an initial current in the inductor. So we need to evaluate that. I of 0 minus needs to be calculated. This is just before change. That would be 5 volt divided by, inductor will be a short circuit. So basically there will be a 0 volt. This is the 0 ground here, 0 volt ground. Inductor is a short, so that potential will be 0. This potential will be 5 here. And 5 divided by 0, 5 amp. 1 ohm, that will be 5 amp. This is your initial current in the inductor. Then we will resort into building the model. Here's the model. Allow me to check my time. 5:05. 8:05. Okay, we have 10. Okay. So let's build our model.
this is the model. You have 1 ohm, you have a step, you have a constant voltage 10 here, like a 10-volt battery. If you have a constant voltage there, it will be then 10 over S. That will be this, its Laplace transform, because the Laplace transform of 1 is, or step, unit step is 1 over S. 10 units of step, it will be 10 over S. And you need to replace the inductor with its series model. So we get that as LS, which boils to 2S. Then you have the Li0, its series voltage source here, negative and positive there. L0, Li0 minus here. Work this out, it is equal to 10 volt. And finally the 2 ohm, and that's the voltage here, V of S. And this is our reference ground, 0. So I can apply conveniently a node analysis at that point, sum of the currents at that point. So here we begin. Voltage here minus voltage there divided by 1. So you get V of S minus 10 over S. Voltage is 10 over S divided by 1 plus voltage here minus voltage here, which already that voltage is a minus 10. So it will be Vs, V of S minus of minus 10. Note please polarity here. That's a plus, this is a minus, so that point is a minus. Minus 10 divided by Ls, which is 2s. And finally, V of S over 2 equal to 0. Rearrange it, and you get V of S equal to 10 over 3, 1 upon S plus 1/3. That is clean cut available in the Laplace table, because 1 over S plus A, S plus A translates to e to the power minus 8. The exponential. So obviously, answer would be V of t, lowercase v of t, so these are all upper V's, will be 10/3 of e to the power minus t over 3. A is 1/3. That is your solution, and that means the answer would be a curve that looks like it will go up, but then eventually will go down to 0. T, this is the V of t, and this will be 10/3 of a volt. Indeed, that's what is going to happen. The voltage will be eventually decaying down to 0, because when the voltage becomes steady next here at 10, again, inductor will go into a short circuit mode. It will be a short, carrying a current, but bigger current this time, because now you have 10, you have 10 amp. So I of 0 will be 10 amp once it is high. So if it goes down again, it goes there, another story. You have to start with the initial condition that is left in the end of this period. So that is what we would expect, indeed, as the voltage of VLS. Okay, so this has been said. Let me see, what's the time? 10:19. Okay, there's enough time to explain 2 of the basic theories in Laplace. It's called initial value theorem, final value theorem.
I'm keeping these pictures here so we can make a reference to that very quickly. The proof of that is in the book. I'm not going to spend time proving those, but just telling you the application. Okay, initial value theory. Well, this theorem says that if you're interested to find out what is f, say it's a function, function of time, but if you want to know immediately at 0 plus what is the value, while you have the Laplace of that function given, how can you deduce from the Laplace of the function, like this guy here, from Vs, how can we deduce that initial value? And I'm going to apply here and show it. So the theorem says, take f of s, multiply by s, and take the limit as s approaches to infinity. In other words, get the limit of s times f of s for s approaching infinity. This should give you instantaneous value of the function in time domain at the time 0 plus. Let's see about this guy. We know what is the instantaneous value. Look at that 10-third here. O plus. Okay, multiply s with that function. It will be 10 over 3 multiplied by s over s plus 1/3. Okay, what is the limit of this when s goes to infinity? It's a very easy one. Yeah. Well, imagine s is a very large number, like a million. Top is a million, and the bottom is a million. So the ratio is almost like 1 for large s. Therefore, the answer is 10/3. Very easy. So we just got that function off of this solution. 1/3, that's the value of that. Next, you can apply to any function, no matter how complicated it is. You've got the function by s, determine the limit of the function, but the product as s goes to infinity. Not the function, but the product of s with the function. Next is the final value theorem. So let's keep again this equation here handy so we can refer to. This is called final value theorem. It's very useful. You will need it again in control engineering. And it is a good thing to check. Final value theorem. If you want to know what is the steady state value of the function as time goes by, here is how to observe that. F of infinity, okay, so as t is approaching to infinity, is equal to limit of s times f of s, same thing, but this time as s approaches to 0. Okay, let us apply to this equation. Your v of s is 10/3 1 upon s plus 3. So what is the limit of 10 over 3 multiplied by an s here? 1/3 as s approaches to 0. This is the v of the infinity. I'm going to obviously 0, 1/3, 0 at the top, 0 over 0, it's just 0. Check here. See that curve? It eventually goes down to 0. That is the meaning of v of infinity or f of infinity. Okay. So in this first part, I reviewed for you the concept of initial values in the inductor, capacitor, resistor, solved 2 examples for it. I explained the initial value and final value theorems with example, and I explained what is the impedance. So let's take a break and then come back in, let's say 10 minutes, okay? Because I'm going to cut from the other end by 5 minutes. So 10-minute break. So we will see at 8:25.
9:40.
Okay, we are back, and let us continue with the work. So in the first hour, I went over the stuff which is extremely important. Be sure that this stuff like this will be in your exam, at least 1 or 2 questions. So make sure that you study all those examples and the solution to homework problem that I gave. Let us now continue with the rest. Yeah. Definition of a transfer function. What is a transfer function? It is pretty generalized. This is called the transfer function. If you have a system, a circuit, whatever you name it, and you subject the system into an input, x of t input, for example, a voltage that drives the circuit, and as an input voltage is applied to the circuit, you have all the nodes here and there. Each one will acquire some kind of a voltage. You pick one of those points and you name it my output, one of the nodes within the circuit or system, and you call that y of t. definitely when you put x of t as a function of time, generally, you're going to get a voltage there or a current there as a function of time. If it was a mechanical system, if you put force into the system, y of t could be a point in the system. For example, position of an object, position of a platform in response to the force. So there would be a relationship between the position of that platform or object versus the applied force. And there will be a differential equation that relates them to each other, which you would have applied Laplace to that differential equation to create the function. So it's pretty general, the transfer function. X of t is the input, y of t is the output. Assuming that initial condition in the system is 0, which kind of eases the analysis, then the ratio of here, if x of s is the Laplace of was the Laplace of y of t, then the ratio of y of s over the x of s, output Laplace over input Laplace, is called h of s, the system transfer function. System transfer function, TF. Okay, so that is the general definition of a transfer function of a system. However, there are a few laws about it. If you happen to have one system, system number 1, and a system number 2, system number 2, and the system number 1 has its own input, x1 of t, creating its output, y1 of t, and the output of that becomes input for the next one, x2 of t, and then this is the y2 of t. Then it can be shown that the y2 of s over x1 of s, in other words, the output Laplace over the input Laplace, because output is a time function, input is a time function, they're cascaded. The output Laplace over input Laplace will be simply the product. I showed you know how to do it. It's very simple. The product of the two. That's it. They will multiply. So the transfer functions will multiply in order to calculate the output Laplace against the input Laplace. This is a very useful law. What happens if you have more in series? Simply keep multiplying. From input to the final end, as many transfer functions that you have, which will contain poles and zeros, those are like rational functions, multiply out, and that will give you your total thing. Then, if you want to know what is the output in response to the input, you've got this product for each transfer function. You can get the Laplace of the input, multiply for the waveform that you're feeding in, and then you can calculate the output Laplace, inverse transform it, and then you can get the function of time. You will figure out what will be the time behavior. Another variation would be often you apply a simultaneous input, and then you have two outputs, and then you combine the two outputs, add them up. That happens in control engineering. Although there isn't much mention of that in the book, in that section, but you know what? It is just a shortcut to control engineering stuff. It's good to know. Here, if you had a system 1 and a system 2, and you were applying a common input, x of t, and you were getting a y1 of t, y2 of t, but then the two outputs we're adding, we're combining together, then what will be the final output? Y of t. It's very simple to know that. This is a simple time functions you're adding. So yt is y1 of t plus y2 of t. And here you have the x of t applied to that point. Therefore, if yt is the sum of the two, y of s will be the sum of the Laplaces of the two functions. You can say that. Y of s is equal to y1 of s plus y2 of s, y2 of s. Because, Laplace of a sum is equal to sum of the Laplace of individuals with property. Now, based on that, you can show that the Laplace of output to the Laplace of input, because each one of them will be Laplace of x multiplied by the transfer function of the individual one. The overall transfer function, y of s over x of s, will be the sum, h1 of s plus h2 of s. That's it. So look, if they are cascading, you will multiply them together. It's like amplifiers and having gains. One amplifier has a gain of 10, the other one has a gain of 5. What's the total gain? If you cascade them, it's 10 times 5, 50. You're multiplying the transfer function. That's what we're doing here. One is 10, the other one is 5. But if you have poles and zeros, now you get a more complex, plenty of zeros, plenty of poles. If they were adding in this fashion, and you want to account for this whole thing with an equivalent transfer function, you wanted to describe it with a single one. This will be the single one, the sum of the two. So you will take the two functions, you will add them, summarize them into one unique function. And that will be the equivalent of the transfer from one point to the other. That's it. So this is the story of the transfer functions. It's Laplace of output over input. Cases when they are cascaded, you multiply. Some rare cases, you won't see it in this course, but later you will see. If they are fed with a constant input, but their outputs combined, it will be the sum of the two. One important thing about the transfer function is this. Suppose you have a transfer function here. Y of s over x of s is h of s. All right. The output Laplace over input Laplace, you already determined, maybe by analysis, that complex impedance concept. Now, suddenly we want to know what will be the output response if I put in Vm cos omega t, some kind of a sinusoidal input as x of t. And I want to know what will be the output y of t as Vo cos of omega t plus theta. There, plus theta. In other words, you apply a cosine function as a phasor to the input. In the phasor, this would be Vm angle 0. You want to know what kind of a phasor will come out of there. What will be the magnitude, amplitude here? What will be the angle, phase angle shift, leading, lagging, or what? How do you do that? Via the knowledge of transfer function. Very simple. This is how you do it. You simply will substitute for s the j omega in the h. So s will be substituted by j omega. For the y of s, you will substitute Vo angle theta. That's for y of s. This is the output phasor description of y of s, not time domain, but specific time domain, the sinusoidal, cosinusoidal, the phasor description. For the x of t, you will substitute Vm angle 0. So if you know what is your Vm, you can, and you know what is your frequency, you can calculate the h of j omega. It has a magnitude, it has an angle, and then you can determine, compare it against the VO theta. Magnitude will be output amplitude. The angle will be phase angle. So this is how versatile is transfer function, the S. You can immediately from S deduce the phasors, the j omega. Okay, so that is the description of the transfer function. Now let us start by coming up with examples. So I have another example for you. Actually, before doing that example, let me give you an account. What is the system impulse response? Here, let us say you have a transfer function here, h of s, given, and then you have y of s, output Laplace and input Laplace. So we know that y of s is over the x of s is equal to h of s. Regardless, what is the shape of the waveform? Ratio of the two Laplaces is going to be a fixed function. That fixed function is called the transfer function given. Now, often systems are expressed by their impulse response. What is impulse response? Of a system. Okay, impulse response means that you take your x of t, and you apply literally an impulse. It's a theoretical complex concept equal to delta t. But you can actually make practical impulses to the system. For example, if you have a system that has certain slow time constants, like 1 second, 2 seconds, 3 seconds, and you want to apply a delta t, 1 unit of impulse. So remember, it's a slow system. Its time constant is a second, within the second. If I create a pulse of 1 millisecond, 1000 volt, one 1000 volt, 1 millisecond, this could serve in the analysis of the system almost like an impulse, because its timing is very, very small compared to the time constant of the system. So it will be considered that theoretical delta t approaching to 0, because it is narrow. It should, because delta t is only theoretical concept. Its width is infinitely small. Well, we don't have infinitely small. 1 millisecond. 1 millisecond will be infinitely small if the response of the system is several seconds or several tens of seconds. It will be considered an impulse. This is a unit impulse. You multiply the area, you get the area. Multiply 1000 volt by 1 millisecond, 10 to the minus 3.
and that's one unit approximately considered a delta T. An input voltage impulse applied to the system. So, what is the impulse response of the system given the transfer function? The Laplace transform of the delta T from table is 1. Laplace transform of the step is different, is 1 over s and going, okay? So check with the Laplace transform table. Laplace transform of the delta T is 1. So if I apply an impulse to that system, what will be the output? Okay. Then y of s, the output, will be equal to h of s. Because that would be denominator here, this will be a 1, h of s. So what is then our output? Y of t, well, simply inverse transform of h of s. So the bottom line is impulse response of a system is the inverse transform of the transfer function. Inverse transform of the transfer function. And that will be the impulse response of the system. So if you had, for example, a system like 1 upon s plus 1, this is considered like an RC, an R and a C, with a 1 ohm and 1 farad, 1 over s plus 1. The impulse response of that would be equal to inverse transform of 1 over s plus 1, which is e to the power minus p. That's a 1 second. That going down to 0. It will rise to 1. If you could apply a unit impulse to that circuit, this voltage. If you apply 1000 volt for a narrow duration of 1 millisecond, the approximate solution to the output of the RC circuit would be, boom, a spike like that, exponentially decay. Decay time will be pretty slow in comparison to 1 millisecond, because the time constant is 1 second here. So that is kind of a concept of what is impulse. Impulse is like a kick to the system. Mechanical impulse would be like a kicking and seeing, what will happen, like a boom, and then you see how it did it. You see the board, look at that, and then there was an oscillation there. You saw that. I think I can see it. So it just oscillates and then eventually decays. So this is considered as the oscillatory decay response. It is definitely an oscillatory and decay. Maybe there are more modes in it, combination of few frequencies because it's a distributed body, but eventually that is considered an impulse response. Okay, the reason that I explained it, I need to give some physical meaning to what is convolution. What will be convolution? So you're going to need. So remember, I said, although it didn't show in the handout, but here is what is the impulse response. What is impulse response? Impulse response of a system is y of t equal to inverse transform of h of s. That's it. Inverse transform of h of s. So if I had an RC, which its transfer function would be straight away 1 over s plus 1. Its inverse transform of that, which is e to the power minus t, would be the shape of output voltage across this capacitor here, if that is the y. Okay, now let us go into this last example, example 3, which is pretty much assuming all energy storing elements have 0 initial energy. Okay, find then the output.
Okay. Example 3. So we have a 2 ohm, a 4 Henry, inductance equal to 4 Henry, a capacitor there, C equal to 1 farad, and a resistor there, R2 equal to 2 ohm, and it is subjected to a ramp input coming like this, increasing. This is a ramp input. The ramp is, or we can say, E of t. The E of t is t ut, so it's a unit ramp. It means it is rising 1 volt per second. Slope is 1 volt per second. We want to determine the output voltage here, VO of t. What will come out of here? Given that all initial conditions are 0. It means the system has no energy, no prior stored energy. Okay, let me remind you. Do you recall what was the energy stored in an inductor? And don't forget that. W 1/2 Li squared. You need to have current in an inductor to have energy. You remember what was the stored energy in a capacitor? 1/2 CV squared. You need to have voltage across the capacitor to have energy there. Okay? So when a system is starting from rest without energy, it means there was initially no current and there was initially no voltage. If it was a mechanical system, there was initially no movement, no kinetic energy for the mass. It was like starting with initial velocity of 0. And if its position was somewhere, its initial position was 0. Those are the initial conditions. No initial condition. When it comes to solving problem with 0 initial condition, and or somebody tells you get the transfer function, simply it's a very happy moment because the models will be the symbols. Look what the models are. Look at the picture. Replace Laplaces for every single one. Laplace of E, Laplace transform of E of t is Laplace transform of t ut from the table 1/s squared. You get it from the table. So there is a source in here. The value is 1/s squared. You replace it with 4s. There is no series voltage because there is no initial current. It's the easy one. Capacitor, there is no series voltage with it. It is 1/CS. CS, like 1/j omega c. CS. C is 1/s. You have a resistor to call this ground for reference, and you want to know what is the voltage there. VO of t. Okay. If this was any voltage like E of S, you could calculate everything in terms of E of S, and eventually you could figure out VO of S over VE of S. It will give you the transfer function. Okay, so writing the nodal equation. So write the nodal equation. Let me tell you, there are many ways of solving this problem. You don't have to always write the nodal equation. You can use laws like voltage divider rule. Here is how to do it. You can call this E of S S squared for it. So imagine that that's a voltage source. How do you see voltage across this branch? If you could combine the two in parallel, the two combined in parallel appear series with this. So one can quickly write the transfer function of voltage here in terms of ES. VO of S would be equal to 2 parallel with 1 upon S divided by this 2O, that 4S, plus the parallel combination, 2 parallel 1 upon S. Okay. Then you can carry out the algebra. 2 parallel 1 over S, it means 2 times 1 over S over 2 plus 1 over S. Get that, paste it here, and that will be, and then multiplied, of course, by E of S, the voltage divider. And then you see immediately transfer function comes out, VO of S over E of S. Take E of S to the bottom here, denominator, as a ratio. You will get your transfer function of the system, the transfer function. I didn't do it that way in this handout because I just wanted to show you apply a voltage here, ramp, what will come out of here. But that is the usefulness of the transfer function. You can come up with more general kind of, function, the transfer function. Treat it, apply the division rules, voltage divider, current divider, name it. All the rules will work. However, let's continue with our analysis based on what I have given to you. So I'm erasing this bottom. Know the equations. So that voltage minus this voltage divided by that impedance, that voltage, Laplace of that voltage divided by the Laplace of this. Of course, now this should be named VO of S. So VO of S minus 1 upon S squared divided by a whole lot, that divided by this, that divided by that. You equate it, you get that equation that I wrote for you, which simplifies to VO of S equal to 1 upon 4 S squared plus S plus half. Okay, it brings it down into that. Again, this is a double pole in the origin. That one is a complex pole. Complex pairs. Of course, conjugate pairs, they're always. Proof of being complex is this. Get the delta of that. It is 1 squared minus 4 times of half. That is minus 2. 1 minus 2 is a minus 1 under the radical. So we get complex poles. Once you detect you have a complex pole, so your strategy should be made accordingly. You cannot split them into real parts. So instead, you will have VO of S equal to generalized A over S squared, B over S. That's for the power, the duplicates one. This is a double pole. So you have a term here, you have a term of S, kind of, it is inside that function. Then plus C S plus D, another constant, divided by S squared, S plus half. Okay. There are many ways of determining A, B, C, and the D. Basically, you know what you can do. The general way would be again, merge all the terms together. I didn't do it that way. I did it by the number method, but it can be done in a general way. Merge everything together. In other words, add them up. s squared. We've got s squared times s squared plus s plus half. And then start creating the numerator based on the a, b, c, and the d, all of them together. So that divided by this, you will get a times s squared s plus half. Okay, this whole lot divided by that cancels s, so you get b s squared plus s plus half. That. You divide that denominator, common denominator, with the s squared s half, s squared stays in. So you multiply s squared by cs plus d. Okay. Having done that, you will start grouping the numerator in terms of the descending powers, the highest power that you see here. The highest power is bs cubed. So don't have room there to show you. Let me see if you can see this level. You will start grouping them. Let me go back one line high. I will write it with a different color so it will be, you can distinct them here. Look at the s cube. I have a term s squared times cs, that's an s cube. Coefficient is c.